Hello, I'm Bikash Mehta, and today I will be talking about the application of numerical linear algebra in modern control. Like, why do we require numerical linear algebra in modern control? What is the significance, and how can we utilize the numerical linear algebra in order to manipulate the state space metrics that come from the dynamics of the system? So today, I will be talking more about introduction to the modern control. What and why do we require modern control? How can we represent any dynamical system in state space, and how can we manipulate all those matrices, and how do we find the controllability and observability based on the rank of a matrix? How can we do the stability analysis by finding the eigenvalues of any state space matrices? And lastly, I will be talking about the optimal control, like how do we need to find optimal control gain in order to minimize the cost function that comes from the Ricardo equation. So I will be talking all these topics in the upcoming slides. So why do we require modern control, and what is actually the modern control? So modern control is an advanced tool and technique that is used to design, analyze, and implement a control system in dynamic environment, because we see a lot of things that comes into play in the dynamic environment. We need to include a lot of parameters, a lot of state, because the classic control only deal with the single input single output system. But in real world, what we know that we have a lot of multiple input multiple output system. Basically, for example, like for the auto steering mechanism of any car, it take a lot of input from cameras like front camera, rear camera, side camera, and it have a lot of output. Like it need to control the steering, like turning left or right, applying the brake and de-accelerating the car. So we can see that even a simpler mechanism for auto steering will require multiple input multiple output system. But in classic control, it can only deal with single input single output system. So we you can think of like a wing control design of any aircraft, like it is way too complex than that of the auto steering control of any automotive car. So here I have outlined one example for single input single output system state space representation. You can see over here. And for the multiple input multiple output system, the state space representation matrix is over here. For this one, we only have one input there, that will be u1 or x1, that is whatever it would be. So I will be talking more about this in the upcoming slide. So why do we require more modern control? As I mentioned earlier, that classic control can only deal with single input, single output system, but modern control can deal with multiple input, multiple output system. On top of that, it also can deal with the non-linear dynamics, uncertainties, and integral, the complex control objective, which obviously classic control can't do. On top of that, it also utilizes state space analysis, so that we can be able to better comprehend the system, the description using state variables, and we can later on modify and change in order to maintain the control objectives. So here is one example of mass spring system. This is a mechanical system, and this is our second order equation of motion for this system. But what happens, like especially in modern control, what we do, we decrease the order of the system into the first order, even though the system is in second order. As you can see that this equation of motion is in second order, but what I have done is like I suppose x1 as p and x2 as p dot, and p dot is also the x1 dot. And I know that x2 dot is p double dot, and p double dot we can find from over here. So that p double dot is this. And now the state space representation, this is in first order differential equation. You can see that p single dot is x1 dot and p double dot is x2 dot. So we can easily reduce the second order differential equation into first order state space representation by this process. So I am going to find either the system is stable or not by finding the eigenvalue for the same state space metric that I have found in the previous slide. So putting some arbitrary values of k equals to 10, c equals to 4, and m equals to 2, I have found my state space matrix. And later on, I can solve the characteristics equation to find the eigenvalues as -1 plus -2. Since all the real part of eigenvalues are negative, so the system will be stable. If any of the eigenvalues is positive, then the system will be unstable, and if all the eigenvalues is zero, then the system will be critically stable. So here is one application of numerical linear algebra, that is, as I studied the diagonalization in numerical linear algebra, it is used to find any matrix function. So by this expression, we can find any matrix function using the diagonalization technique, because if A is diagonalizable, we can represent that A by using this term, where P is the matrix that consisting all the eigenvectors, and D is a diagonal matrix that consists of all the eigenvalues as their diagonal elements. Here is the proof, like how I get to this in that expression, because this FA function come from the Taylor series expansion, because I already know that A is diagonalizable, so that I can write this expression as this one, because this is a scalar, I can put that inside, because D is the diagonal matrix that consisting all the eigenvalues, so that I can write this as matrix form in this way, and because this is scalar, we can write this as over here. So I already need that this is now the Taylor series expansion for that eigenvalue. So I can replace all these with this function of all the eigenvalues, so that we can find this beautiful expression to find any matrix function. Similarly, this is one example to find the matrix function in the exponential term. There is exponential of any matrix function, and there were J1, J2, Jd. These are all the eigenvalues. So now I am going to talk about the controllability. So basically, what is controllability? The controllability is like a system is said to be controllable when the desired output is obtained by applying the specific control input. So that what it actually means, that we can control that system based on the input. So based on this example of state space representation, I have got my controllability matrix as this one. Since this matrix is not full rank, because one of the rows is zero, the system will be uncontrollable. And for this second example, because I have found this controllability matrix and this matrix is full rank, so the system will be controllable. And for the observability, it is the system's ability to measure or observe the system measure. So we can find all those states. So for this, similarly, we have to find the observability matrix based on this expression, like C, CA, and if it's 3 by 3, then it can go up to C, CA square, and so on. So because this matrix is full rank, as we can find from here, so the system will be observable. So I will be talking about the Riccati equation. So in modern control, Riccati equation is fundamental tool to use to solve optimal control problem, particularly in the context of linear quadratic regulators, where it provides the optimal control gain by determining a positive definite, that is P matrix, that minimizes the quadratic cost function, effectively balancing state deviation and control report. So we will be talking more about in the later slide. So here, what is required equation, and what are the parameters that we do have in that equation? So basically, it consists of A matrix, that is state transition matrix, B is control input matrix, Q is state cost matrix, and R is control cost matrix. So I will be talking more about this. So here is the Riccati equation. This is the Riccati equation, that is also Riccati equation. This is our state space equations. This is state cost function, that is J, that need to be minimized. So in MATLAB, we can simply use this LQR function in order to find like optimal control gain and the P matrix. And after finding the P matrix, we can use it to find the K matrix that uses the MATLAB. So here is the Riccati equation derivation, because the system is defined by this equation, and this is our state, that is our cost function. So what value of u minimizes g? Actually, we need to find that. So as we know, P is a symmetric matrix, so P equals to P transport, and this is J, this addition and subtraction, and after completing this, we will just get this one. So it will again be the same expression, and after substituting this term in this divided this in term over here in x dot ax plus ps, and then we can get this as this form, and after substituting back into this into g, that j, that is the cost function, we get this good expression. So grouping all these two together, the we get our cost function as this one. So this is the same as this. So as we can see, this expression does not depend upon the u, but this expression do depend upon u. So we need to complete the square of this term, and upon simplification, we get this term as this expression. So after plugging back into the original cost function, that is this one, so we get the cost function as this term. So what we have already said, that we need to minimize this cost function. So for the minimization, this should be equals to 0, and this need to be equals to 0. So if we happen to this equals to 0, then here is the algebraic Riccati equation, that is algebraic Riccati equation after equating it with the 0, and after comparing this term with u equals to minus kx, we get the k as R inverse B transpose P. So once we get the P value from this expression numerically, we can substitute that equation in this expression to get the optimal control gain. So to conclude my slide, numerical linear algebra is obviously a fundamental tool in modern control system, enabling efficient and reliable computation for any controller design that I already mentioned in the algebraic Riccati equation. And we also can find a lot about the system behavior, like stability depending upon the eigenvalue, controllability, and observability. So it also has a wide range of field that include robotics, aerospace, because in modern control we need to do a lot of control mechanism, and for that we require the numerical linear algebra. So yeah, we have a lot of application like complex and data driven more control mechanism, and for that we will surely require a more intricate numerical linear algebra. So here are the few references that I have used to prepare my slide, and thank you, that's all from my side. Thank you.